Thank you. I really appreciate the opportunity to come and talk to you. For y'all, I'm at the National Soil Dynamics Lab. If you're familiar with Auburn, you probably know it as the Tillage Lab. It's right there in the middle of the campus, but it's actually part of the United States Department of Agriculture. I've also listed here some of the other scientists that are involved with this particular technology that I'm going to talk about. The two listed, Alexander Kavastrik, Galina Yukovava, Steve Pryor, and then are with the ARS lab, and then Nicholas Sadjoin and Brian Chin are Auburn University's. And we have a joint, it's actually an Auburn University patent for some of this technology. So anyway, so I want to start out just talking about carbon. Carbon is the basis of all life. It's equivalent, that's what organic matter is, it's carbon. If we want to measure organic matter, we measure carbon. And it's part of all functions that are in the soil. So understanding our carbon levels is fundamentally important to the productivity of soils. And so it's a strong determinator of what the quality of the soil, the productivity of soil. So anything we can do to increase our organic matter is going to make our soils more productive. And so we think that an accurate soil measurement is essential to try to get to learn how to manage your farms. So we've been developed a technology. There's a short movie here.
Have you ever planted a seed, watered it, given it sunlight, did everything right, and nothing grew? It's likely that the soil didn't have the right nutrients for the plant to grow. Healthy plants rely on a healthy soil. So how do we know how healthy our soil is? Growers have long used a process known as dry combustion analysis, or core sampling, to find out what nutrients their soil has and what nutrients it might need. By taking core samples directly from the earth, scientists measure the amount of organic carbon. Carbon is the main component of all biological organisms. The more carbon present, the healthier the soil. This process can take as long as 2 months, or even 6 months in some cases, which means growers have to wait for the information they need now. That's why USDA's Agricultural Research Service partners with academia and commercial developers to find innovative solutions for problems just like this.
Over the years, we have been trying to develop innovative ways to measure soils and specifically soil carbon. And we teamed up with scientists from Brookhaven National Lab, which is part of the Department of Energy, that focus on nuclear science and measurement using gamma rays to determine content of different materials. We worked with them to develop new ways of using their nuclear physics technologies in soils. This collaboration started many years ago. The first publication came out about 2008, in which we started looking at metrics where we could have equipment that could actually measure that concentration of carbon in the soil at the atomic level. This particular technology allows us to scan the soil without actually taking the soil physically from the ground, and so that we're actually measuring the carbon as it is in that particular place.
The value of this tool is far-reaching. A process that used to take several months now only takes a day and provides data more precise and comprehensive than ever before. It should help to maximize the effectiveness of fertilizer, ensuring it's placed only where it's needed. And because every neutron interaction has its own signature, it will be able to map other kinds of elements found in the soil too. This may be beneficial for carbon sequestration efforts and the production of feedstock. Perhaps the next time you plant a seed, the soil you'll be using will have been analyzed in the same way, and this time, you'll finally have the healthy plant you wanted after all.
Okay, so I want to show that to you because it's obviously written for a very general audience. It's produced by the ARS, so the soil fertility is a little bit oversimplified, but it gives you the overarching idea of that we have a tool that we can run across the field and develop carbon. So I just thought I'd go into a little bit about how the technology works. We basically have a neutron. It is generated. It hits the nucleus of an atom. That atom becomes excited. And then it goes back to a less excited state by releasing gamma rays. And then these gamma rays, there's lots of different types of gamma rays that could be produced. The one that we're focused on is the inelastic neutron scattering, because that particular one has a very significant signal for carbon. It can measure a lot of different elements, and the important thing is that each type of atom has a separate, once it's excited and produces gamma rays, those gamma rays have a specific energy signature that can be determined, that can be seen. So the idea is that we have a neutron generator, shoots the neutrons into the ground, it interacts with the atoms in the soil, they produce gamma rays, a certain portion of them goes back up to the surface, we measure with gamma detectors, and then but when it measures it, it's doing a large volume of soil, not just one particular place, and so we're looking at a volume of soil, not just a small portion of soil that you're analyzing in the lab. Those particular gamma rays then can be separated into their energy spectrums, and then carbon has a very distinct one that allows us to then calculate what the concentration of just the carbon atoms are in the soil in that volume. So, of course, I wanted to say that we have measured this very extensively with traditional soil sampling measurements. I've taken soil cores and measured them with our in the laboratory, and we get very, very significant correspondence to those rates. It works very well to measure the carbon. The thing you have to remember about carbon is you can't just take one sample, you got to take the increments, and we've done that to show that that whole volume is represented by the sample if we did it in the lab. So it's a non-destructive sampling. It's in situ, so there's no sampling preparation involved. We can get multiple elements. It measures a large volume of soil, which is quite different than any method that you can use for other than this. And then it also has a scanning capability. And the reason that's possible is that gamma rays are moving at almost the speed of light. So as we're measuring this, we could actually move across the field, and the instrument never knows it's moving. It's just increasing the volume that it's measuring. So instead of measuring one basketball-sized area, we take that basket-sized area and move it across the field. So we're actually, where we've settled on, we're measuring about 1 acre with 6 inches deep is basically the area that we have for our one measurement block. So basically we took this inelastic neutron scattering, put it on a mobile platform, so we'll call it MENS for short. This is what it looks like in our current iteration. So the idea is you would take this scanner, you go across the field, you would drive across it. You didn't have to do it in a pattern, but obviously you probably would. After you've gathered that data, we have it GPS reference so that we block up the sections that come from each into a block grid, and then we get an average for that whole block grid that then we can turn into maps. And we can do this the same day. And so I think this is just kind of summary. It's basically the same thing that each block is measured 1 acre, but we don't. But we envision that you would say do a block would be any size that you wanted to measure. You've just measured an acre of the land that's in that block. But we think maybe 6 to 8 acres for each one of our individual blocks would be what we settle on. Then add that with both density measurements, and you can get this tons per acre that you need of carbon. So, and then you can generate maps just like this. These are actual maps that we created with our equipment. The one on the left is carbon. That was actually a peanut farm. It's some land that I own myself. And the middle one is where we measure potassium. That was up at in the Piedmont station for the university. And the one on the right is actually where we could measure moisture in that same peanut field. So, but we wanted to talk about carbon credits, and we've had we've talked, already heard some about it, but I just wanted to talk a little bit more about it and how this technology can play into a role in that. So the basic idea is that with raising levels of CO2, it goes up into the atmosphere, captures heat in that atmosphere, and we have rising temperatures globally, or global warming, or global change that's becoming more and more of a concern. I don't know how y'all feel about about global warming, how important it is, but one thing's for sure, it is a political issue, and therefore it's going to be an issue for all of us. And so it's an issue that we play a role with in agriculture. So the idea of cap and trade is where we get the concept of carbon credits. And the idea is that policymakers will put a cap on how much CO2 can be emitted. And there's two ways you can go about that, right? You can just say, whatever energy you're using, next year you can only use half as much. And so, but that's not going to really work. So a better approach is to say, we're going to put a cap on how much energy, but if there's a way that you can reduce how much CO2 you are producing, or you can capture CO2 from the atmosphere, as we heard about the new technologies, then you have created a carbon credit that can be sold to somebody who needs to still emit carbon. So, there's two ideas, as I just mentioned, is the prevention, and that's probably a safer way to go, because if it's never emitted, there's no way for it to be released back into the atmosphere, right? And so you could do that by reducing your fertilizer use, for example. If you can document that you use, a third as much fertilizer, then the carbon that went into making that fertilizer and the potential for it to emit CO2 and nitrous oxide can be a credit. But the other one is to remove carbon, and that's where we get into these types of technologies, or building up organic matter in your soil. So, and I think I've already talked about this. So the basic idea is if the federal government caps emissions, then certain industries would have to buy the allowance or offsets to continue to be able to use energy. So the truth is, almost every industrialized country in the world has already adopted a cap on emissions, except the United States. So everywhere else in the world, there's already a very active carbon trading market. And so there's well established, because those industries have to remain under that cap, and if they want to exceed that, then they have to buy a carbon credit. So it exists already. It's just whether we're going to adopt it in the United States. We have a very underdeveloped source of selling carbon here, because we don't have any caps that are regulated. So, but if y'all have listened to the news, y'all know that there's a lot of political pressure to start the United States to reduce our carbon emissions. Just this week, the president has started some executive decisions to move us towards those reductions. They've made commitments to try to bring in carbon limiting policies. So, but what that's going to look like is still, it's up to debate. We're not sure what it's going to look like. But like I said, there's already carbon credit markets in other parts of the country that we can participate in. So, why should we care about it in agriculture? Well, I think I always say we're part of the problem, we're also part of the solution. If agriculture is accused of creating 20% of the CO2 or global greenhouse gas emissions in the world, well, you can't be accused of 20% of the total emissions without having a target on your back. So it's going to be important for farmers. So whatever legislation that they finally decide on, it's going to impact farmers. It's going to be fuel for your tractors, it's your nitrogen fertilizers, it's how do you raise your cows. All these things are going to be part of that equation. And so, but the other part of it is it also is an opportunity for us because we can play in the game of carbon sequestration and then potentially have a source of income for the carbon reductions that we can sell that other industries are going to be forced to have to buy. So carbon sequestration, like I said, it equals organic matter. The plants take up CO2 out of the atmosphere. It moves down through the soil. And then becomes part of the organic matter eventually. So anything that we can do to increase the organic matter in the soil, it's going to reduce the CO2 levels in the atmosphere. And so, so once you increase that organic matter, then you have sequestered the carbon. Now we'll have to say that comes with the caveat that there's the permanency issue there. If you go to no-till and then 2 years later you plow it all up, then it's not permanent. So there is that thing that you need to keep in mind if you ever want to try to sell your carbon, or it'll just be discounted so it's less valuable. But if you can document it, then you can sell it. And so the trick is, how do you measure it? Because it's a lot more difficult to measure soil carbon than our normal soil fertility measurements that we develop on concentration. You know, roots will explore the whole soil. If the nutrients are there, they can find it. But with carbon, we're trying to measure change in mass. And so we have to keep the different layers involved in how much actual carbon is there, and also track how it's changing with different places in your field. So some of the things to remember is that small changes are important. If you look at an acre furrow slice, you know, an acre of land 6 inches deep, that's a standard bulk density, that's 2 million pounds. When you measure, multiply anything by 2 million, you don't have to have a very big change in that soil carbon to have a big number that you're looking at. Normally, our soil samples we're measuring, when it goes to the lab, it's got 20 to 200 milligrams, just tiny, tiny things about the size of your little finger. Tip of your little finger is what's there going to equivalent to an acre of 2 million pounds of soil. So it's doing that large volume, I think it's important. Also, you have to remember that soils, most of the carbon is going to be in that top 6 inches or 30 centimeters. But it changes dramatically with depth. It drops off tremendously. So you need to be able to do different increments to make sure that you're not you're overestimating or underestimating actual amounts of carbon that are there. It also changes with soil types, and the potential to sequester carbon is going to change with the soil types. It's going to change with climate. Obviously, cooler climates are going to have higher levels of carbon than we do down here in the southeast. And so, and it's very common to change the carbon levels across the field. I mean, that's the whole principle of precision ag, right? You don't have a uniform field. You have fields that are changed across it. And one of the main things that are part of that is the levels of organic carbon in there. You know, you inherently know that lower part of the field where you don't have as steep a slope is richer and has higher organic matter. Well, those are the kinds of things you're going to have to keep in mind, and why we want to be able to map the soil if we're going to look at carbon sequestration. Processing is a very difficult thing. If you're going to do sampling right, you can't just go punch a few holes. You're going to have to take grid sampling, and then once those grid points are made, you have to cut the sample into the different increments. You have to dry the soil, grind the soil, and then weigh it into these little tiny bullets I was talking about, and then you're going to run it through a skipped one here, soil testing lab. You know, the instruments that there are $75,000 to sit on that bench, and they can do, say, 100 samples a day. but that's one of the reasons why it's so expensive. So what we found is that we did a survey of all the different labs that do organic carbon, and we found that the average cost is $21 per sample. You need 4 or 5, at least 2 or 3 samples per spot if you're going to do the carbon. So we had an economic evaluation done the same way you would if you were doing your business. You were going to operate a business where you were going to provide carbon sequestration data. And we used the basis of taking a grid sample farm, about 300 acres, that you could take that you were going to take 1 core sample per 3 acres, so 100 cores. We use this as kind of basis because of my 30 years of experience taking soil samples. That's about as much as a crew can do in a day. And so if we looked at that with all the equipment involved, it comes out that you were going to need $12,000 to do the soil sampling in that one field, or $48 an acre. And remember, you got to do that twice. You got to do it when you start your practice. You got to do it 2 or 3 years later to see how much carbon is there then, because it's the difference that you're selling, not that you implement those practices, is how much carbon that you now have in the soil that you can sell. So it's a very inexpensive process. So we think that the technology we have that can do the, eliminate the lab work and produce the maps will make this a viable practice. And that's where a company called Carbon Asset Solutions came along. They are licensed to technology and are building a company to do just this. They're actually a carbon credit marketing company, and they have decided to use this technology as a method that they're going to use to measure the soil. They're actually located out of Australia. Like I said, they have a established carbon market in Australia, and we actually have a crew now out of Canada. Again, Canada has a well-established carbon credit marketing, and so whether we ever do it in the United States or not, they already have a market for it. They are going to implement it there. But so they're taking this technology and commercializing it. And so, let's see, I think. So the important thing is when they do this carbon credit, they will measure the field. The farmer will have to decide what kind of changes he's going to implement that's going to build up carbon. They'll come back several years later, measure it again, and then they will take charge of marketing that carbon, that difference, and then share the profits with the farmer. That's their business plan. And the nice thing about they will create certified carbon credits because they have actually measured it. This is a $1 billion of money in this. Some people say even trillions of dollars, because everybody who uses energy is going to have to play along and participate in these things. And so it's going to be traded just like any other commodity, just like you trade your peanuts. It's going to go up and down in value for that carbon, but the expectation is it's going to go up in value because there's, as we grow, as we need more energy, we're going to have more carbon credits. And then they're going to be harder and harder to come by as we get already used to easy ways to do it. And so that's going to raise the price. So it's a $1 billion industry. They think that but it's one that hopefully farmers can be a beneficiary of. So the current estimates that they think they can do about 64 acres an hour, 640 acres a day. That's what they're targeting, over 10-hour day. They'll have a relatively short period that they can do, because obviously you can't run this scanner across your field when your corn's growing, right? You can't run over it. And so you're going to have to go in those periods of time when you're not going to hurt the crops. They're based their evaluations on 4 years, that they can use these carts for about 4 years before they have to replace them. I would hope they could use them longer than that, but that's what they're basing their evaluations on. And they think they can be less than 10% of the cost of what it would be needed in doing the traditional grid sampling. So, as I said earlier, organic matter helps everything about your farm. There is no negative about increasing your organic matter. Water holding capacity. soil fertility, everything's improved with what you increase in organic matter. And then at the bottom end, you increase your farm productivity, environmental sustainability. And then hopefully, we'll also be able to increase farm income. So with that, that was all I was going to say. I'll be glad to try to answer questions.